In the notes, and I believe in the book as well, but in my lecture, I included this and I talked about it briefly in class, the three C's of credit. So I want you to just briefly recap that, put it in your own words, just type into this text box. Okay. And then the other thing I have in this intermediation one is thinking about, back to lecture 5 actually, thinking about this great quote from this economist Arnold Kling. He says, the public wants to issue risky long-term liabilities and hold safe short-term assets. Financial intermediaries accomplish this by doing the opposite. So what do financial intermediaries do? They hold as assets the liabilities of the public, and then they issue the short-term assets of the public, which are their liabilities. So what the heck does that mean? So let's go to the Excel sheet and I'll show you. So I've got basically two T account balance sheets, one for the individual and then one for the bank. And I want you to take these items down here, and what you'll do is copy and then place it in the proper place or places in these balance sheets. So cash, for instance, well, that would be an individual's asset, right? And that would also be a bank's asset, wouldn't it? Yeah, cash is nobody's liability. Well, technically the central bank's liability, but that's kind of meaningless. Okay, and then, a personal loan. I want you to do this with all of them. I'll just run a couple examples. Well, for an individual personal loan, what would that be? That would be a liability, right? Where did the loan come from? It came from a bank or some financial intermediary, and that would be that bank's asset, right? So I want you to put each item in the appropriate place. Some will go on both balance sheets, some will go on only one balance sheet. So see if you can go through all 12 of these things and put them in the appropriate locations up here on the two balance sheets. All right, moving on. Let's deal with some present value situations. And I got a nice little book out of the got a nice little problem out of the textbook here. So it's proposed that Steph Curry, basketball player for the Warriors, will become a free agent at the end of this NBA season. Suppose that Curry is considering two possible contracts from different teams. Note that the salaries are paid at the end of the year. The interest rate is 10%. If Curry is indifferent between the two teams and only looking to maximize his income and wealth, which contract should he take? Now these numbers might be, on the small side, but it doesn't matter. We're just trying to understand the concept here. He's got two different payout streams, and we want to compare them side by side. And I think in your problem, the sums of the payout streams are equal. I don't know if that's true in my alteration here, but let's see. I'm going to sum them up like this. And yeah, it does, yep, because I did a monotonic transformation of them, actually, I remember now. So they're equal in their sum, but is one preferable to the other because their different amounts are paid at different periods. So what we would want to do here is take the present value of this year's payment plus the present value of this year's payment plus that present value plus that present value and add them all up. Now I could make you do 4 different present value functions, but let's face it, I'm not that cruel and nobody has that much time.
I ain't got time to bleed.
So let's go ahead and do a shortcut, which is Excel's NPV function. Now, what NPV will do is just given a rate that you plug in, and what did we say the rate is here? It's 10%, so let's plug that in first. That's the first argument, right? Comma. And then the values that occur in the future. Now, notice here, the signing bonus is paid today. So the $1 million, that we don't need to take a present value of that because that occurs right now. That is in present value terms. So we only need to take the present value of the year's first year, second year, third year salaries. Okay, and then to have a complete present value, we'll add the value of the signing bonus. So I'm going to run the NPV function, the rate, and then the string of future values that occur at 1 year intervals, and then close that parentheses, and then the signing bonus. Okay, so I'm going to run that for the Boston contract offer, and then I'm going to slide that over here to run it for the Portland contract offer, and then we're just comparing apples to apples now because these are both in present value terms. So the sum were equal, but the Portland one turns out, and let's see, let's maybe box that in to indicate that that's the better offer. It's worth about almost $500,000 more. And why is that? Well, notice that more of that income occurs earlier in the Portland contract, so it's pulled up in time, and that's why its present value is higher. The present value of money that occurs way out in the future, remember, is lower because it would take a smaller amount of money invested now to grow to that future value. Okay, moving on. This is one, I think we did one like this in class. It says, against my advice, you played the lottery and one, oops, I need to change these numbers. I'm going to say you win a $10 million jackpot, and your options are a $5 million lump sum or a $500,000 annuity for 30 years. There we go. All right, assuming a 7% discount rate, I'm going to plug that in right now. Which option maximizes my present wealth? Okay, well, 5 million is already in present value, right? I could have that now. That's a lump sum. So I just need to calculate the value of the present value of the $500,000 annuity for 30 years. It has no future value because it pays out completely, but it does have a annual payment of 500K. Let's say the annuity is received at the end of the year, and we're just going to run a present value function on here with this data: rate, payment, payment, PV. I didn't give you a type. Oh, I did give you a type. That's going to be H14. You could just type in 0 if you want to. Okay, so the annuity is going to be worth 6.2 mil. That's better than 5 mil, so maximizing my present wealth via the annuity, right? And with an annuity, there's usually a survivor option. You might be saying, well, I might be dead in 30 years. Watts. Okay, but you could assign it to your wife, husband, children, etc., and therefore you'd still maximize the the benefit of that income stream for you and your designated heirs, right? Okay, bond pricing. I hope this is very familiar, and we're just going to reiterate a very important and core lesson of interest rates and asset values here. So find the current value of a 5-year 8% coupon bond with a face value of 1,000. We know that the face value is the future value, the principal or the par. The rate is 5%, right? We're discounting it at 5% because it says the current rate on similar assets is 5%. The number of periods left is 5 years. And the payment, an 8% coupon bond, it pays 8% of the $1,000 par or principal. So it pays you $80. And here we're just going to, for simplicity, assume annual coupon payments. Type end of year. Let's run the PV. That rate, that number of payments, that number of periods rather, that payment, that future value, and that type. And I have the payment positive, the future value positive, so it's going to give me a negative present value. If you don't like that negative present value, two things you can do. You can just put a minus sign in front of the function. Okay, now let's run the same data here, but over here we're going to have a current interest rate of 6%. Interest rates go up, that makes the value of the bond go down. And let's run it one more time. Control C, Control V, but now we have an interest rate of 4%, and that makes the asset value go up, right? So the change in value from part A is this value minus the initial value. The change in value from part A is this value minus the initial value. And down here, don't forget this, it says interest rates are what? Inversely related to asset values. I'm giving you that answer. I want you to remember that. If nothing else, just be able to say like a parrot.
Same question.
Interest rates are inversely related to asset values, and I'll give you a cracker. But hopefully you'll understand why, because you're familiar with the present value math that's driving that. Let's look now at a more kind of real-world valuation problem that a small investor might confront. And this is for valuing a rental property and thinking about making capital improvements. So starting off here in the left panel, we've got rental property is expected to earn $13,600 yearly in net income. So we've kind of already subtracted out the cost of management, maintenance, vacancy, etc. And it says you expect the unit to last another 20 years before needing total replacement. That is, its value will depreciate basically to zero after 20 years. And if you think that's unrealistic, let me tell you from experience that renters can be very hard on property. So the value doesn't necessarily fall to zero, but what you want to think about is that you need to remodel it or revamp it, rehab it, and you're basically starting over in certain cases. So that's not entirely unrealistic. But even so, 20 years out, the present value is going to be pretty low anyway. Okay, so your opportunity cost of capital is 10%. Calculate the appropriate market value of the property. So we're going to run our present value function here by putting in all the arguments stacked in the order they appear in the functions in Excel. So our rate is, what did we say, 10%. Our INPER, 20 years. Our payment is 13,600. And then our future value, 0. Now, as I told you, that it's not going to matter that much. Even if we said it's going to have a residual value of like $50,000 or something 20 years out, you'll see that that's not going to make a huge impact on the present value. How do we do the present value? PV function. Plug in the arguments now. Rate, in per, payment, future value. And then we'll go with, I usually just go 0 for type. Not going to matter too much on a 20-year asset. Okay, present value comes up negative, so there's two ways we can fix that. We could just either flip the sign on the present value function, or we could flip the sign on payment. So whichever you like to do. I like to flip the sign on the function, because then that keeps all the numbers in my list positive. Okay, so the thing is worth $116,000 roughly under these assumptions. Now let's move on. Now, of course, we can think about how that's sensitive to changes in our threshold rate, right? If the interest rate goes up, the asset value goes down. That's Bocephus, right? If the useful life goes up, the present value is going to go up. But notice it didn't go up. If I added 10 years to the useful life, the present value only went up by what, $14,000. So the farther out you get in the future, let's add a lot of time to it. If I added 70 or 80 years there, the present value only went up another $10,000. So that those far out future periods, they don't really contribute that much, because you have so much time to accumulate that sum of money. And again, if we had said there's a salvage value of like $50,000, notice that doesn't add much either, because that's occurring 20 years out. So I like to, for safety's sake, when I'm valuing a property, I'll say, let's just depreciate it all the way to 0. Let's just say it's going to be totally dilapidated and need total replacement, total updating at the end of our investment horizon. Okay, let's move on to the middle panel now. What is the maximum amount you'd be willing to pay for renovation that would be expected to increase the useful life by 30 years? That is, after the renovations, you expect the unit to last 50 years. Okay, everything else is the same. So I'm going to copy over all the data. So I'm copying and pasting, Control-C, Control-V. But then what I'm doing is altering my lifespan now to 50 years. Again, I'm going to copy. I could run the PV function again, but I'm too lazy to do that. I'm going to copy and paste it. And notice that because I used relative references, all the references have slid over to column F here. And so now the appropriate valuation is 134,800. Let's call it 135. Okay, and then it says, what's the maximum amount you'd pay for renovations? Well, I'm not going to pay more than it adds to the capital value, right? So I'm going to say, here's the ending capital value. There's a beginning capital value. That is my renovations budget. I'm not going to pay more than 19 grand for the renovations. If I pay more than 19 grand for the renovations today, I'm going to lose money in terms of present value term, capital value. Okay, let's look at one more scenario with our rental property. Right-hand panel. What happens to the unit's capital value if the Federal Reserve can successfully reduce broad interest rates, and hence equity yields, by 120 basis points? Basis points, how basis points work now. It's 1.2 percentage points. So we're going to use the original 20-year life from panel A over here. So let's copy this over. But now we're changing our threshold rate, reducing it by 120 basis points. So that's going to be from 10% down to 8.8%. And notice what that did. That increased the capital value. When interest rates go down, say it with me, Bocephus principle, asset values go up. And what's the percent change? Well, we'll run a calculation there. That's going to be the difference in the capital value. So subtract the 2 and then divide it by the starting point. So that's an 8 point. That's a 9% increase. 1.2 percentage point drop in the interest rate caused a 9% increase in capital value. Pretty significant there. And does the Fed ever move interest rates by 120 basis points? Oh, yes, they do. Go over here to Federal Reserve Economic Data, which is a really good database from the St. Louis Fed. We'll use this quite a bit going forward in the class. And look what the Fed did with interest rates here from the recession of 2001, where the benchmark federal funds rate was about 6.5% going into that. And then look where it was coming out of that, 1.75%. So the Fed cut interest rates here by like almost 400 basis points, 500 basis points. So yeah, in a pretty short span of time, in like less than a year and a half. So can the Fed move interest rates 100 basis points, 200 basis points? Absolutely. Okay, the only other thing I want to do here is calculate the change in the asset value. So that's just going to be the initial value minus the starting value. So the value change is plus $10,000. The percent change, I already did that there. I just copy that, about 9%. Okay, one more challenge for you is I like to think about investment returns for any kind of asset people get involved in, speculate in. And a lot of times people feel really good about their investment returns. I'm using air quotes right now. But they're really just nominal returns and they're not accounting for inflation. So I like to be a party pooping economist and say, hey, what's the real return there? Oh, maybe your hot investment wasn't so great because you didn't factor in inflation. Never do. So here's some scenarios that we're going to work through where we'll take the nominal returns, but then we'll factor in inflation and see what the real returns actually were. So I'll give you some kind of a explanation up here. I'm going to give you the present value and future value and the investment time frame. Now we're going to use the rate function. So if I have the present and future value, but I don't have the rate, Excel can do the math to find the rate. So it says the PBS TV show Antiques Roadshow features expert appraisals of art, furniture, pottery, and other such antiques. Often people buy antiques speculatively, hoping their value will rise and then will turn out over time to be a good investment. Or sometimes people just buy something because they thought it was cool and then they're pleased to realize that it went up in value. Deploy your knowledge of asset valuation using Excel formulas to calculate the investment return in the following cases. So panel A right here is going to be this one right here. Mary Louise Salas bought a Federal period chest from an antique store in 1975 for $300. Okay, I just realized I had a bunch of data in there. We need to start fresh. Okay, so Mary Louise Salas bought a Federal period chest from an antique store in 1975 for $300. In 2005, Lee Kino appraised it at $3,000. Calculate Mary Louise's rate of return, assuming she sold the chest in 2005 for the appraisal value. All right, so that's going to be A right here. So appraisal year minus purchase year. From 75 to 05, that'd be a 30-year span. If you're not sure about that, just have Excel do the math for you. No shame, Excel's the world's greatest calculator. Payment, this asset does not yield annual income, so there's no payment. That's going to be the case with all of these. PV is the original purchase price. What did she pay? $300. And then FV is the appraisal value. 30 years hence, $3,000. So what's her rate of return? Well, let's run the rate function. And notice what the rate function does. Basically, it just has all the time value function arguments here that we would have to know in order to calculate the rate. So the in per, and notice I always keep these stacked in the same order. The payment, which is 0. The PV, which was 300. The FV, which was 3,000. And the type will go with 0. Now, there's only one other thing here. Excel asks you for a guess, because what Excel does is works with an iterative process. I think you don't technically have to do this, but you can start, you can enter a percent, 0.1, 10%, or 0.05 or whatever. I don't think Excel makes us do that. Let's see. No, they don't. And so if you enter the guess or don't, it doesn't matter. The reason this came up as a number error is because one of these has to be negative. Excel has this quirk where money that's an outflow has to be negative. So I think if we make the present value negative, there we go, that'll make it work. So you spent basically $300 originally, and then you gained back $3,000, presuming you sold it now at the appraisal price. So your rate of return is about 8%. So the person might be feeling pretty good about that. You say, well, that's only an 8% return. You probably could have done better with financial securities, especially once we factor in inflation. So let's jump down to this box here. It says, in case A above, 300 in 1975 had the same inflation-adjusted buying power as $1,089 in 2005, according to the BLS inflation calculator. And by the way, if you're curious about that, there's a website here. You just Google BLS inflation calculator. The Bureau of Labor Statistics are the keepers of the Consumer Price Index, and they provide you a handy little tool here to work through. Of course, we can do this in Excel, we know that, but we can just do it here much easier. So 1975, and it was what, $300, has the same buying power as what in, we said 2005, right? That was the year she sold the chest. Okay, $1,098. It's going to vary a little bit whether you use the beginning or end of the year. So we said $1,089, close enough. So what we want to do is rerun that scenario over here. I'm going to copy everything, paste it, but now I'm going to put the purchase price in terms of $2,005, which was $1,089. And oh, her real return has now shrunk to a paltry 3.44%. you would have done better in almost any other asset class, bar maybe bank CDs. But if you're thinking about a 30-year investment horizon, you might as well go for add some risk to your portfolio and go for some returns that have a long run, a much higher long run yield. Okay. So you can do the same thing with Bud Simonson here in panel B. He bought a 1931 Frankenstein movie poster at a garage sale in 1991 for $25. In 2015, Craig Flinner appraised the poster at $2,500. Calculate Bud's rate of return, assuming he sold the poster in 2015 for the appraised value. Okay, so what's the time frame here? We went from 91 to 2015. Let's just have Excel do the math. 24 years. No payment on that asset. What did he buy it for? $25. What's the appraised value? $2,500. And let's run the rate function. Now I don't need to type the whole function in again. I've ran it here. I've got the data structured in the same manner, so I can just copy and paste it. Control C, Control V. Well, that's a little bit nicer looking return, 21%. But again, we have to account for inflation. So it says $25 in 1991 had the same inflation adjusted buying power as $44 in 2015. So I want to rerun this. And instead of the $25, it's going to be minus 44. And so his real rate of return is 18%. Okay, now that's a respectable rate of return. I still wouldn't recommend buying antiques to make money because it's so hit and miss. It's really high risk, and investing in a diversified portfolio of securities is probably going to be your best bet in any case. But it's fun to think about real returns, and you can maybe shatter people's assumptions about how they did on various assets when they're only thinking about nominal returns. In many cases in Antiques Roadshow, they show people with a apparent investment gain, but once you factor out the inflation, they actually have a loss. And people are suffering from money illusion if they think they made money on antiques, that they paid $20 for and is now worth $200, but it's 30 or 40 years later, where the value of the dollar has gone down by more than the percent gain in the nominal price of the investment. So anyway, there you go. There's just some applications to think about rates of return and practice with using Excel, world's greatest financial calculator and tool that we will use as much as humanly possible in this class. You're now in a position to take care of homework too, and I will catch you later.